Hi, this is going to be lab number 6, digital logic and gates. So what we're going to be doing this week is building a circuit using digital logic and gates. We've got a bunch of NAND gates here. So these are 2 input gates that give you not the AND of the inputs. Okay, and that's indicated by the little dot at the end there, and also by the part number. Now these gates aren't individual elements that we're going to be adding. They come in a dip socket here, which contains a number of different pins, and this actually has 4 different NAND gates in it. So this is the, not sure you can see that, this is the SN74 series. So this particular one is an HC00N, and the HC tells you that this is a high-speed CMOS implementation, and the 00 is the code for a quad 2-input NAND gate, which is exactly what we need. All right, so we're going to need a pin diagram to know how to hook this up and where the gates are in here. So on the pin diagram, you're going to see a little dot on one side, and that tells you where the number 1 pin is, and on the dip socket here, that corresponds to this one side of it that has a little divot there. So you see the other side doesn't have it. So that means that pin number 1 is right there, and that's how we're going to be able to line that up with this diagram, like that. So what we're looking for are where the inputs and outputs are. So the inputs to the gates are with A's and B's, that's the 2 different inputs to each gate, and the output is Y. So this means that input number 1 and input number 2 are going to be NANDed together to give us output on pin number 3. And that's also listed down in this table here, so you can see 1A gate 1 input, 1B gate 1 input, 1Y gate 1 output. It's listing whether it's an input or an output. And the other thing that we're going to need to hook up before any of these gates are going to work is the power and the ground for this circuit. And that's on pin number 14, VCC, that's where you put the positive voltage, and ground on pin number 7. To know how much voltage you need to apply, you need a different page of the data sheet, and that's this one here. These are the specs. So here it tells you recommended operating conditions, VCC supply voltage. It needs a minimum of 2, nominally 5 volts, and a maximum of 6 volts. So we have to be careful not to put it up to 6. Ideally, we're going to give it 5 volts. Now the high-level input voltage, this is telling you some information which is going to be important for later on in the lab. For us to recognize that something is a 1 on the input, we're going to need, so a logical 1, a true, we need a minimum of 3.15 volts. And that sort of depends on what VCC is. So if we give it a VCC of 6 volts, then the minimum for it to recognize as a 1 is 4.2. If we give it a power supply of 4.5, then it's 3.15. If we only give it the minimum input power supply of 2, then anything above 1.5 is going to be recognized as a logical 1. Now the low-level input voltage is a little bit different than that. So here it can't be higher than this for it to be recognized as a low. So if we give it the 6 volts input, then anything below 1.8 will be recognized as a low. And part of what we can investigate is what happens in between there. So what if we have it at a 6 volt high power supply, but we give it an input voltage between the highest that's supposed to be recognizable as a low and the lowest that's supposed to be recognizable as a high. So let's say like a 3.5 or a 3 volt input. What's that going to do? We'll be able to figure that out with some testing. We've got our circuit set up here. We've got some LEDs that we're going to use later. And we've got the non-breadboard plug wires being used to plug route the top parts into the rails on the breadboard. Okay, now in order to insert the dip sockets here, these don't really fit in regular spots in the circuit. You might be able to, you can put them in there, but then you're just shorting 2 pins that shouldn't be shorted together. So that's what this center rail is for on breadboards. So we can go over, let's say, anywhere here, and then connect it from the top to the bottom side of the breadboard there. Okay, now we're ready to go. We've put the little the little divot on the left side, so that's going to make it easier for us to read. Pin number 1 is going to be at the bottom left then, and it's going to go around 1 to 7 back to 14 on the diagram. So that means on the breadboard 1 to 7 and then up to 14 on the other side. So we need to power this circuit now, and that means we need a high, whoops, and that's why you shouldn't go and clamp them, because they can only bend a couple of times. So this one's garbage. Okay, we'll need our VCC, which we're going to put on pin number 14 there. Maybe we'll put that a little bit closer together to make it easier to see. And then we'll need our ground on pin number 7, which is this one. Okay, now we can do some tests. In order to make the output easier to see, we could be measuring it with a voltmeter, but it's easier if we hook up a light-emitting diode. These have 2 different pins, one of them longer than the other one, so if it comes straight, then you can just bend it a bit so that you'll be able to put it into the circuit. And the longer one indicates where you want to put positive voltage if you want current to flow through it. The diode will only let current through in that direction. So the current that you would get going through it is going to be too high unless you also put a current limiting resistor in series with the diode. So here I have a 1 kilo ohm resistor, and we're going to do that. We're going to take our 1K and the diode and connect that to one of the outputs that we want to see. Let's suppose we want to look at output number 3 there, the output on pin 3, which is the output of logic gate 1. Then what we'll do is jump from number 3 over to somewhere else. Suppose we jump over to this empty spot there. Then we can connect the LED from that rail to ground. Okay, so we've got a connection from pin number 3 through the current limiting resistor, and then that's on a rail with the LED connected to ground. So this is going to go on only if the output of the circuit is high. Right now we're not putting anything on the inputs, so the inputs should be indeterminate. Okay, so we're going to get our current supply ready to go. As usual with this particular kind of DC power supply, we'll turn on the power when it's not hooked up to anything and check that the voltage is about right. So now we've got this set to about 5 volts. We can now turn the current down and then up just a little bit and short the input and output to measure what the current is. So let's set it to about maybe 100 milliamp just to make sure it's not too high. Okay, so we'll go and plug in the power supply and turn on the power. And right now we're not giving any input to the circuit, and the output is sort of changing between low and high a little bit. It's not really, you saw it go low for a bit, wasn't making up its mind there. In order to make the input more defined, we can tie that input to either to low specifically. So let's take one of the inputs and the other one and put it to low. Now we are getting high in this case as the output because we want because the input to the NAND gate terminals are both 0, and if we AND 0 and 0, then we get a 0. So if we NAND them, we should get a 1. For us to see what the output will be in response to putting one of the inputs high, it's going to be more convenient for us to connect this top high rail to the bottom rail. And now those are connected too. So we can jump over here and put one pin to high. Should still be a 1 output. It should only go to a low if we tie both inputs to high. And there we go. So with both inputs high, it's stuck to low. If we put one of them to low, then it drops down. Okay, and there's the functionality of the NAND gate. So now we're going to try and build this circuit and verify that the output is what we think it should be. So for that, we're going to need 1, 2, 3, 4, 5, 6 NAND gates, which means we don't have enough on this one chip. So we're going to need another chip in there. This is the same kind, and we're going to put it in to this other spot over there, and also power it up. Ground on pin 7, and VCC on pin number 14. Okay, so first thing we can do is verify that the logic from this part works and have that as our output. So maybe we can make the gate number 1 there, the one that we've already wired up because we've got an LED already hooked up to its output, and then we won't have to move that around. So let's call this gate number 1, and then we can use, let's say, this one is gate number 2, and this one is gate number 3, and we'll hook that up. Okay, so gate number 2 on the dip socket is down there. It looks like 4 and 5 are the inputs to gate number 2, and gate number 3 is up on the other side from 8, 9, 10 on that circuit. Okay, so for gate numbers 2 and 3, we're going to need both of the inputs connected together, so that'll be a little bit convenient if we go ahead and jump those wires right at the start. Maybe we'll turn off the power while we're changing around a lot of these input wires, just in case we accidentally hook something up to a high or low that we shouldn't. So we can use this jumper to get in at the inputs to gate number 2, which are pins 4 and 5. So 1, 2, 3, 4, and 5 here. We need those connected together. And then we're going to use one of them to be an actual input to the circuit. And let's just put that to ground for now. Maybe we can pick a color to be our inputs. So something sort of unique. Let's pick blue, perhaps. Yeah, there we go. Okay, so that blue is going to be the input for number 2. Then what we can do is take the output from that, and the output from number 2 should be tied to the gate number 1 that we have here. And output from number 2 looks like it's on pin number 6. So we'll connect this input to gate number 1 over to pin 6. Great. And now that's connected. Maybe we'll go around this input so it's not in the way. Okay. Now, next up, we need to wire up gate number 3, and that's here on the top. So similarly, we need both inputs to gate 3 to be tied together. We'll use another yellow wire for that, just to try and be as neat as possible. This is definitely going to become a bit of a mess of wires, but we'll give it our best shot here. So that's going to be connecting the 2 inputs, which are 9 and 10, together. And then we'll pick another blue wire for that input, which this time is S. We can wire any of those to, let's say, low again for now. Great. And then we'll take the output of that, which is pin number 8, and we'll jump that over. Oh, we already have a wire for that, actually. That's this purple one, which was the other input to our gate number 1. So we'll jump that over here to the output of 3, and there we go. Okay, so now both the blue wires should be setting the inputs to gates 2 and 3, and then the output of that should be on this gate, gate 1, which is still tied to our LED. So we can do a bit of analysis to check how this output should behave as functions of those inputs. So we've called this one S and D. So since we're putting S to both inputs of this NAND gate, that means this wire would be holding not S, and this wire would be holding not D, and then we're going to be NANDing those, so that means we're going to get the NAND of not S and not D, or by De Morgan's law, we'll get S or D as this output right there. Okay, so what we should verify is that this LED is connected to an OR between those two inputs. So let's power everything on and see what happens. We've got both blues tied to 0 and the LED is off. So that looks good. Let's put one to a 1. It's on. The other one's still at 0. If we put this to a 1, it stays 0. If we put, or sorry, it stays as on. So now we've got, we verified all of the input states except maybe 1, 0. Yeah, okay, so we've got logical OR. So if we have 1, 0, 1, 1, or 0, 1, then it's on. But if we have 0, 0, it goes off. Okay, so it works. We've demonstrated our De Morgan's law, and we've demonstrated hooking up these 3 gates and verified that it's right so far. Even if the question didn't ask you to output this, this state right there, it's probably a good idea for you to confirm something after you've put in a few gates, just to make sure that it's all hooked up correctly, because as you can see, this can quickly get out of hand. We're also saving ourselves a lot of effort by color coding the wires, so knowing that the blues were the inputs makes this a lot easier to go and check later on. So now that we've got the first half of the circuit done, we can plan out how we're going to add in the rest of these gates. So let's go ahead and label this one number 4, and then we can put these 2 over here as maybe the inputs on the second dip socket. So how are we going to call that? Maybe we'll call that like B1 and 2. Okay, so that means the final output will be the output of B2, so the number 2 output on the second dip socket there. So we can go ahead and wire up an LED to that output right away. That'll be pin number 7 on that one. We put our current limiting 1K resistor, and we've got the LED here connecting up the positive end of it to where the positive side is going to be, and then connect the other end to ground. There we go. And so there's our LED hooked up. Just to verify that that part's working and that this dip socket is working the way we think, we can NAND those inputs together. It's taking both inputs and tying them to low, and it looks like it's actually not working correctly. So why would that be? Well, let's first test that this LED works. Ah, you know, it looks like I missed the LED. So I put it into the, it's definitely not going to work if I don't connect this into the right spot that that resistor is connected to. So let's just move that over. Okay, we're all good. One of the reasons why you want to check that right away, can you imagine if we'd finished hooking up everything and then it wasn't working, how many different things there would be to check? Just would be a nightmare. So definitely good that we sorted that test case out early. Test early and often, you know. So we'll plug that into the output of this gate on the second dip socket, and that's working, and we can verify that it is indeed doing logical AND. Yep. And then nodding it with our NAND connection here. So when we put both inputs to high, that's when we get the output to 0. Okay. So that's going to be our final output, and we're going to need the inputs to that to be tied together. And now it's just going to be inverting. So if we put a low, we'll get a high. If we put a high, we'll get a low. Confirmed. And we'll make that being fed in from the output of the previous gate. Gate number B1. Now we can wire up B1 to be connected to the output of, let's see, gate 1, which is connected to our LED there. And that'll be right over here. Same terminal as the LED is on. And then the other input of gate B1 can be connected to the output of gate 4 up there. So that one, we're going to have to go across the circuit and verify the output is pin number 11, and that would be this one. So now we can wire the inputs of that to be made up of our new input, input number A, so we'll get another blue wire there. Wire that to low for now. And the output of number 3. Because of the way we numbered this, we know exactly which one that is. That's pin number 8 there. So we'll take that output and connect that over to the other input of gate 4. There. And now we should be reproducing our final logic here. So we can analyze it and see what we're going to get. So this is A up there, which means we're going to have a NAND of A and S on this terminal here, or by De Morgan's laws again, not A plus not S, or S, and then these two together are just going to be ANDing those two together. So we're going to have A bar or S and S or D, which is equivalent to S or A bar D. Okay, so let's check that it works. So, got a little bit of flickering here, usually indicative of a bad connection, but so far seems stable at this point. If we take, so this is this blue wire here on the bottom was the input to gate number 2, so this is our D. So right now we have A bar is true because A is connected to the ground, and then D we've made true. And let's see, the output has not gone to true actually, so let's see if we can debug what's going on with that. First let's mess around with some more of these inputs and see what we can make to happen. So this one that we added in the middle here should be S, which means that should go to true. The output should go to true no matter what S is, no matter what the other two are doing, if S is a true. But it looks like it's not. So there might be something strange about the rest of our outputs there. Ah, you know, we've got something disconnected here. We've got a green wire disconnected. And let's check. where that was supposed to go. So this was connected to the output of gate number 1. Oh, I've also got a bad connection to the low power of the entire circuit here. Okay, so the low of output number 1, and that's supposed to go over to input B1, and right now, indeed, there's nothing connected to that, so we'll connect that. Okay, now we've got our output showing up. So let's see if we've got, oh, this wire is just not very good here. Doesn't want to stay into that spot on the breadboard. Let's try a different spot on the breadboard. Okay. So, all right, everything looks good. We'll connect this to a low, and then everything goes low. Connect it to a high. They both go high. All right. Now, if we were to connect A to a low, then the output here should go off, but this part shouldn't care because that doesn't depend on A. Yep, so verified. Now, while we're at that spot, if we connect our S to a high, the output should go high. Yep, because we're ORing with S. So we've guaranteed and reproduced a few values on our truth table. It looks like the circuit is working. So now what we can do is we can explore how these gates are going to behave if we give an input that's out of range. So I've got 2 more 1K resistors, and I'm going to form a voltage divider using these. So we'll take this and connect that to there, and then we'll go from that input over to ground. And now the center point here should be at half of that voltage. So if we take one of the inputs, like say our input S here, and we connect that over, well, so now input S, you see, is controlling what's going on with the output pin. We can see how that behaves if we connect it to this spot. Doesn't seem to have changed. But what if we had it at low, and now we connect it to that spot? It's gone high. So in this case, the output voltage seems like it's enough for us to get to a high here, even when we're going at this intermediate voltage. But I wonder if that works at all of the different voltage levels. We can go up to a bit closer to 6. You see the output's starting to flicker. It might not be obvious in the camera, but it's flickering a little bit here. If we go to a lower voltage level, then both of them can start to get messed up. So if you don't give the correct amount of voltage to one of the inputs, the circuit can still be kind of robust, but what it considers a high has to be the same as what the circuit before it has considered a high. So that's why being aware of these sorts of specifications on datasheet can be important. If we have a VCC of 6, then you need to give it at least 4.2 volts for it to be considered high. And here we're giving it a voltage of like 3, and it still is outputting a high right now, but that's not a guaranteed behavior. So maybe for a different chip manufactured on a different day or at different temperature conditions, it wouldn't do that. It should be giving us a low guaranteed if we are below 1.8 volts only. But it might be possible for us to get a low if we were to put in 3 volt. So it's not guaranteed what it's going to be behaving as anywhere between this 1.8 and 4.2. And that's it. Thanks for watching.